Hello, so actually let's talk through an example of a hypothesis test. So in the last video you may remember that I came up with a null hypothesis. So I looked at chocolate bars, okay, and I looked on the back of this chocolate bar and I said that the true mean weight of this chocolate bar is equal to 100 grams. Okay, so that is the currently accepted belief. That's my null hypothesis. Now, let's suppose I want to do an alternative hypothesis, and I don't care whether it's greater than or less than 100 grams. All I care is that it's not equal to 100 grams. So this is what I want to test the null hypothesis against. This is my alternative hypothesis. So my null hypothesis is saying, well, I think the currently accepted manufacturer's mean weight of the chocolate is 100 grams. All I'm going to do is go out and test, is the mean weight actually 100 grams? So is it greater than or is it less than? So how am I going to do this? How am I actually going to do this? Well, fairly obviously, I need to go out and I collect some data. Okay, so if I want to test whether something is true, I go out and I collect some data. Okay, now let's suppose I can't physically collect every single type of chocolate bar, namely because most of them have been eaten. Let's suppose I go out and collect a sample of 50 chocolate bars. Okay, so I go out and select a sample of 50 chocolate bars, and I take the mean of this sample. And I find that the mean of this sample is actually 100.5 grams. Okay, it's actually 100.5 grams. So it's pretty close to 100 grams, right? And I currently know that according to the manufacturer, I look up on the website or something, I contact the manufacturer, and they say, well, actually, the sort of standard deviation is supposed to be 2 grams. So I expect some level of standard deviation from 100 grams. Of course, it's not going to be exactly 100 grams, but I reckon it's going to be close, and there's going to be a standard deviation of 2 grams here. So, okay, given this data, how can I establish whether this is enough evidence to say whether it is equal to 100 grams, so the null hypothesis is true, or whether it's not equal to 100 grams? In other words, I'm sort of trying to test it against the alternative hypothesis. So, here is the idea, okay? What I'm going to do is I'm going to suppose that the null hypothesis is true. Okay, so I'm going to suppose that the null hypothesis is actually true. In other words, the true population mean weight of these chocolate bars is actually 100 grams. That's what I'm going to assume is true. Okay, I'm then going to ask the question, well, what is the probability of obtaining this sample then? Okay, so I go out and collect 50 chocolate bars, find that the mean weight of these 50 chocolate bars is 100.5 grams, and I know that the population standard deviation should be 2 grams. So what is the probability of me getting this here? Now, if the probability is small, okay, so if that probability is small, in other words, I've got a low chance of getting this value, of getting this sample data, if that is actually true, then I can say that H0 is probably unlikely. Okay, so it's unlikely to be true. All right, so if I come out with a probability of like 1%, that's a really small probability. And then I can say, well, actually, because I have a low chance of getting this sample data, if the mean weight was actually 100 grams, then I can say that the null hypothesis probably isn't going to be 100 grams, because that's the only thing that we've assumed to be true here. This is categorical data. I can go out and I can work out the probability based on a normal curve. That's categorical data, okay? If that probability is small, then it's probably unlikely that that is true. That's the only thing that we've assumed to be true, okay? So a couple of things here. What do we mean by small? Okay, because small is quite a subjective word. What do we mean by small? Well, we kind of need to decide, okay? And the decision that we base it on is the significance level. In other words, how significant do we want our test to be? Okay, so we base it on the significance level. That's what we mean by small. So in other words, if my significance level is 5%, for example, and again, you can change this, you can change it to 10% or 1% or whatever you want it to be, okay? If you say that whatever this probability that you get out, so when you look at this sample data, and you say, well, what's the probability of obtaining this sample data? If that probability is less than the significance level, then you can say that it's a low chance of happening, then H0 is unlikely to be true. In other words, the true population meat probably isn't going to be 100 grams. Now, just because this probability is so important, okay, because this is literally how we build the test. We literally do this test and we ask what's the probability of obtaining this sample. Because that probability is so important, it establishes whether this is true or not, we give this a special name. And no prizes for guessing what it's called. We call it the p-value. Okay, so the p-value is simply what is the probability of obtaining this sample if h naught is true. Okay, what's the probability of obtaining this sample if h naught is true? Okay, and we call that the probability. So in other words, the result of the test, we've got two options. Okay, if the p-value is less than the significance level, then we can say that the probability of obtaining this sample here is really small. So therefore, we can say that h naught is unlikely to be true. In other words, we can reject h naught. So the mean weight is probably something completely different. It's probably not going to be 100 grams. Okay. Whereas if it's the other way round, if the p-value is bigger than that, then we can say it's a big enough probability value. So therefore, it might be the case that h naught is probably true. So h naught is probably true. Okay, now you notice my wording here. I never accept anything. I never accept anything. I only reject or I fail to reject. So actually down here, I should say I fail to reject h naught. Okay, so these are the two options. You either reject or you fail to reject h naught. The reason why we never accept anything is because it's literally based around probabilities. The whole point of hypothesis testing is that it is based around probabilities. Okay, and even if that probability is small, there is still a chance of it happening. So it's not impossible. So for example, if my p-value, the probability of obtaining this sample up here, given that this is true, is say like 1%, that's still a chance of happening. There's still a 1% chance that this is true, given that this is true. Okay, of obtaining this sample, given that this is true. So even though it's a small probability and we say it's highly unlikely, there is still a chance that it could be true. Okay, so notice we never say accept anything. So we never accept that this is true, or we never ever accept that the alternative hypothesis is true. It's always reject or fail to reject the null hypothesis. Okay, so that's a really key point. So we never accept anything. Okay, we just either reject it or we fail to reject it because it's based around probability. Even if the probability is small, there's still a chance of it happening. Okay, good. So, let's have a look at the example which I used then. So let's actually have a look at this data up here. And I want to establish, let's say at the 5% level, so my significance level is 5%, whether this null hypothesis is we can reject it or we can fail to reject it. Okay? So here is the idea. What I'm going to look at is a normal curve, because I know that this data is probably going to be normally distributed, okay? Because most data in life is normally distributed. So I'm going to draw out my normal curve, and at the moment, my currently believed mean weight is equal to 100 grams, okay? So I'm going to stick the mean weight in the middle there, because of course the true population mean weight should be in the middle of this curve. I'm then going to ask the question, well, given this data, what is the probability that this sample mean here, this 100.5 grams, what is the probability that this 100.5 grams lies in either of these two tails? Okay, or in other words, what is the probability of obtaining a sample which has a mean of 100.5 grams if I collect 50 things in my sample? Okay, so I need to see where 100.5 grams lies in relation to this curve. Now obviously I need to use the central limit theorem here. So if I say that x is the random variable that denotes the mean weight of my chocolate, then before I knew that x was going to be normally distributed with a mean weight of 100 grams and the standard deviation was going to be 2, so the variance is going to be 2 squared. Okay. I then go out and I select 50 things in my sample, so I select n equals 50, this is just the central limit theorem, remember, and I take the mean of those 50 things. So therefore my new sort of random variable of these 50 things is still going to be normally distributed, still should have the same mean, however the variance should decrease, and it's going to decrease by a factor of n. So it's going to decrease by a factor of 50. Okay? So basically what I need to do is look at the standard deviations. Okay, so I'm going to first of all do my test statistic. So at the moment I've got 100.5 grams and I'm trying to see where 100.5 grams lies on this curve in relation to this mean weight of 100 grams. Okay, so first of all need to standardize it. So I'm going to take 100.5 that's my value. I'm going to take away my hypothesized mean, which is 100, and I'm going to divide by my standard deviation, which is going to be 2 over the square root of 50. Happy? It's just going to be the standard deviation. That's the variance, that's the standard deviation. Now if I stick that in a calculator, just very quickly, so I'm going to do 100.5, take away 100, and I'm going to divide by 2 divided by the root of 50. Okay? And I come back with a value of 1.77. So this is 1.77. Now this is a really important value, this value down here. This basically tells me if this was true, if the null hypothesis is true, okay, how many standard deviations, in this case above the mean, is this value going to lie? So it's 100.5. So it's going to lie 1.77 standard deviations above or below the mean. So in this case it's 1.77 standard deviations above the mean. So it's going to lie in about there. Now, because again, this is important value, right? It's an important value. We give this a special name as well, and we call it the test statistic, because it's the value that we've gone out and we've tested. We've collected some data, so it's our test, okay? And we've formed a test statistic. Okay, so in other words, I know that 100.5 grams is going to lie here. 100.5 is going to lie here. Now, just to check, does this value lie in the critical region? So I now need to go away and I need to check, does this value lie in the critical region? Well, just remember, my significance level, I said was 5%. Okay, I said my significance level was 5%, which means that these two tails here have to add up to 5%, right? So in other words, each tail is going to be worth 2.5%, right? So each tail is going to be worth 2.5%. So I've got to split that 5% equally. Okay, that's my significance level. That's when I say that my data which I've collected is significant. So I go in here and I try and find 2.5%. Just remember 2.5% is 0.0250. Okay, so I'll just try and find it for you quickly. 0.250, let's see if we can get it. 0.250, there you go. So it's negative 1.96. So in other words, the cutoff region is 1.96 standard deviations above and below the mean. So basically, if I lie less than 1.96 standard deviations above or below the mean, I can say that my test statistic is not significant. If I lie more than that, so if I lie to the right of that or the left of those values, then I'm in the critical region, I'm in the shaded region. That's where the probability of obtaining that sample is low. Okay, and therefore I can say, well, that is significant. Okay, so either it's significant or it's not significant. In this case, it's not significant, because if you have a look, 1.77 lies less than 1.96 standard deviations from the mean. Okay, in which case the associated probability is big enough to say that that it's not significant. In actual fact, let me just find the p-value for you. So let me just find the p-value. So what is the probability of obtaining a sample which has 1.77? Now just remember that our tables here are cumulative. In other words, you need to look at less than or greater than. So you can't look at the exact probability of obtaining a sample which is equal to 1.77 standard deviations from the mean. Okay, so if I look in my tables, best I can do for 1.77, let's have a look, 1.77 is going to be 0.9616. In other words, it's 96.16%, okay? And of course I need to do 1 minus that, because I'm looking at extreme values. I'm looking at, well, what's the probability of obtaining a sample which is greater than that? Again, this comes back to the fact that I can't look at the probability that x is equal to some value. Okay, I can't look at the probability that x is equal to some value. All I can do is what's the probability that it's greater than or less than. So I choose to look at the probability which is more extreme. In other words, how many data values do I expect to have, so how many samples do I expect to get, which are more extreme than this one? Okay, so p-value is what is the probability of obtaining a sample more extreme than this one. That's another way of interpreting a p-value. A p-value is the probability of obtaining this sample, okay? And again, if it's big, then we can sort of say that it's probably not significant. If it's a small probability, then we can probably say that this is probably not going to be true. But Another way of obtaining the probability, because again the tables are cumulative, you have to look at what is the probability of obtaining a value which is more extreme. So in this case you're looking at a value which is lying to the right of this one. And that comes out as, we just do 1 minus 96.16%, which comes out as about a 3.8% chance. Okay, so the probability of lying to the left is equal to about a 3.8% chance. Okay, so therefore, because you're looking in relation of 2.5%, okay, because this probability is sort of relatively high, so it's higher than the 2.5% critical region that we were looking at, okay, then in which case you need to say, well, do you know what, it's not significant. So the conclusion of the test is that the null hypothesis is failed to be rejected. In other words, it might be that this is true. Okay, so hopefully that makes sense.